Hey everybody, this is a homework assignment for our day 1 lesson. So that's a Monday if you're in cohort A. For cohort B, I would have passed this out on a Tuesday. If you weren't here, you can print out a copy of this and I'm going to go through a little bit of it. Now when you get this homework assignment, you should just have finished an activity, an in-class activity called day Z+1, the aftermath. So it's part of our zombie week list of activities. We had a little packet. We talked about exponential growth, and we're going to build on that here, or just kind of put some ideas together and practice some of those ideas on this worksheet. It won't take you nearly as long as the packet did, but there's some similar ideas that we want to hit. Okay. The first thing that we need to take a look at is how to write an exponential function. Okay. So when you guys wrote your function for your graph that you made for the Z+1 activity, it looks something like this. The population after n doubling periods is equal to 1 times 2 to the n. Okay? And this was how many zombies we started with, and this meant doubling. Okay? Now that's actually a template that we can use for writing all kinds of exponential growth functions. Okay, it looks the generic form looks something like this: f of x equals a times b to the x power. So notice that the x is your exponent. The variable is actually the exponent here. Okay, and a stands for initial amount, or sometimes called initial value. Right, so over here, notice we had like 1 zombie, so there was a 1 in front. That's just how many we're starting with. Doesn't have to be zombies, it can be other stuff, but in this case, we're talking about zombies. Okay, B, this piece, represents what's called the growth factor. Okay, factor is a word that means a number you're multiplying by. Right, so factor is multiply. And notice that we're doubling over here. So that growth factor for our equation that we wrote was 2. Initial value is 1. We started with 1 zombie. Growth factor was 2. We have this repeated multiplication. Okay? If you look at this guy for a second, this is a new function. So it says this function represents the size of a zombie population after X days. Find the initial starting amount and the growth factor. Well, if we go back to our template here, we know this is the initial amount, this piece, and this is the growth factor. So when we look at this guy, we just kind of match up that template. That piece that goes in this position is the initial amount. So that's that guy. So initial also means starting. So initial amount or starting amount is going to be 12. And that's 12 zombies. So in this scenario, we start with 12 zombies. And the population's not doubling, it's not tripling, it's actually growing by a factor of 5. Okay, so you don't have to know this word, but the word for like doubling is multiplying by 2, tripling is multiplying by 3, quadrupling is multiplying by 4. So you could say that this is quintupling, multiplying by 5, but you don't need to say that. It's just growing by a factor of 5. That's another way to say it. So the growth factor is 5. Okay. Now, this question doesn't ask for this, but we're going to have to do this later down the line here. So let's just practice making a table. Okay. So if I had X over here, number of days that have gone by, and over here I have population, P, I can start making a table based on this idea that it starts with 12 and it multiplies by 5 every time. So when 0 hours have gone by, or sorry, 0 days, excuse me, we're talking about days. When 0 days have gone by, I have 12 zombies, because that's my starting amount. Okay, so initial value. Notice that, X is 0 because no time has passed yet. No days have gone by. Okay, now when 1 day has gone by, I need to multiply this by 5. So 12 times 5 would be 60. I'm going to have 60 zombies. After 2 days have gone by, I'm going to multiply this by 5 again, so 60 times 5 would be 300, right? And then after 3 days have gone by, I need to multiply by 5 again. Every time I go up a day, I need to multiply by 5 again. So I need to do 300 times 5, which would be 1,500. A lot of zombies. Okay? So notice this repeated multiplication of 5. Right? Notice at 3 days, when 3 days have gone by, I'm going to have 12 times 5 to the third, because I started with 12, and then I multiplied by 5 1, 2, 3 times. Right? So start with 12, multiply it by a bunch of 5s to get here. So after 3 days, you're going to have 1,500. That's 12 times 5 to the third. Okay, so we're going to try to make a connection between the function that we're seeing and the table that we can make and the graph. Okay, but right now the important ideas are initial value, initial amount, how many are you starting with, and growth factor. Okay, so let's do this one together. We're going to do this front side, and then you'll be able to do the second one because the second one's pretty similar. Okay, so let's read the directions. For the following questions, imagine a population of 5 zombies that's tripling every day. Okay, so tripling means we're multiplying by 3. 5 zombies is how many we have right now, how much we have to start with. We're going to assume no days have gone by. So that's our initial value, or initial amount. Initial amount would be 5, and we're talking about 5 zombies. Okay, and then our growth factor is going to be 3, because every time a day goes by, we want to multiply by 3. Okay, so remember, factor is a word that means you're multiplying by that number. Okay, so a factor of 3 means you're multiplying by 3 every time, and that's how you triple. Okay, so it says imagine a population of 5 zombies is tripling every day. Same idea. Okay, make a table that shows how many zombies would be there after 0, 1, 2, and 3 days. So just like the table we made over here. So I'm going to make a little T table here. Okay, and over here we have X, which stands for the number of days. And over here you can use F for function, or you can use P for population. It doesn't really matter. I think we have been using P's in here. So let's use X for days and P for population. So we have 0 days, 1 day, 2 days, and 3 days. All right, so 0 days have gone by, right? Well, there's going to be 5 zombies because that's how many we start with. We have this population of 5 zombies, and nothing's happened to it yet. Okay, but then we triple. So a day goes by, and we have to triple. So times 3. That's going to give us 15. Okay, and then another day goes by, and we triple again. 15 times 3 will be 45. And then another day goes by, and we triple again, so we have to do 45 times 3, which I think is 135, but let me double check. Yep, 135. Okay, so this is the table, and you don't really even need to do the multiply by 3. I just wanted to show you what the pattern is here.
Oh, there is a volleyball tournament in the AC room today. Bring your friends and have fun. Thank you.
Sorry about that, getting interrupted by announcements here. Okay, so this is my table. This is just showing me the pattern. So let's take a look for a second and just talk about this pattern. Okay, actually, sorry, I was going to write an equation. We'll come back to that in a second. What we're going to do right now is we're going to graph. Okay, so 0, 5 is our first point, right? 0, 5. Now this goes by tens, so 5 is going to have to be halfway in between 0 and 10. That's my first point. Okay, and then I have the point 1, 15. So 1, 15. Again, 15 is halfway in between 10 and 20. So we're going to have to, go halfway there. We got 2, 45. So 2, 45. Here's 40. Here's 50. So halfway in between 40 and 50 would be 45. And then 3 and 135. So here's 3, and here's 135 all the way up here. And we can't even do 4 because by the time we get there, we're already off the charts. You'll notice that these exponential functions tend to grow pretty fast. So we're going to make a nice smooth curve, just like the zombie graph that you guys made in class today. All right, and there we go. That's our exponential growth curve. Okay, one of the things I wanted to point out to you is that this point right here is your initial value, but on the graph, it's the y-intercept. Okay, so where do you see the initial amount on the graph? That's just kind of a way of asking you to make that connection, that this is the y-intercept. Okay, it's right here. And that's true for all the functions. So whenever you see a function, you know the initial value is the y-intercept. Let's take a look at some other functions we've talked about. 0, 12, that's the y-intercept. So this guy right here is the y-intercept. Right over here, when we started out with with one zombie, that's the y-intercept. So if you want to make yourself a note, this a right here, the initial value, the initial amount, is also the y-intercept of your graph. Okay? So that's kind of what's going on there. All right. Let's keep going. Okay, write an exponential function that will give you the amount of zombies after x days. Okay, so remember, the template looks something like this. A times b to the x, where a is the initial value and b is the growth factor. And we already talked about those things, right? Initial amount of 5, growth factor is 3. So our function, if we fill in these pieces, will look something like this. P of n, right? We'll use P for population. Actually, let's use x because we talked about x days, right? X days. P of x, population after x days, is equal to, you got to start with the initial amount. Okay, we started with 5 zombies. Okay, and then we multiply that by 3, and then we have the x power. Okay, this power represents repeated multiplications by 3. So this is our function, but let's just see if we can figure out what that looks like, right? If we wanted to find p of, let's say, 2, what that means is the population after 2 days. So what we'd have is 5 times 3 to the 2 power. Okay? Notice here in the table, if it's been 2 days, I've started with 5 and I multiplied by 3 once and then twice for day 2. Then I get to 45. So if you just double check this is 5 times 3 squared. 3 squared is 9. 5 times 9 is equal to 45. So our table and our function agree with each other. Okay? The way we represent this repeated multiplication by 3's is with that power. So for x days, it's x for the exponent. Okay? Use your function to determine how many zombies there will be after 12 days. Okay? So this is asking us to find p of 12, the population after 12 days. So it's 5 times 3 to the 12th power. I started with 5 zombies, and I've tripled every day for 12 days. Okay? But repeated tripling, repeated multiplication by 3, this is how you represent that. Okay, now we have to be careful about order of operations here. I don't want to do 5 times 3 first because exponents come before multiplication. Right? Remember PEMDAS, our old friend. Exponent comes before multiply. So I need to figure out what this is first, and then I'll multiply that number by 5. Okay? On your calculator, you'll probably have some x to the power of button, something like this. It'll be x to the blank or x to the y or something like that. So I want to do 3 to the 12th power. That's going to be a pretty big number. Okay? And then I multiply that by 5. So that looks like 2,657,205 zombies in 12 days. That's pretty powerful, right? It's pretty crazy amount of growth. So that's how you write a function, and this would be evaluating a function, plugging in a number and then seeing what the value is. Okay? So use that for an example on the second page. You're going to do basically the same kinds of things. You just need to know that template. You need to know an initial amount goes first, growth factor goes second, and then your power. You need to know how to evaluate. You also should know that this number, the initial value, is also your y-intercept. Okay? Now let's use that idea to graph a few functions. So you're going to do these guys, very similar to what we did on the first page. I'm going to show you how to do the graphs on the bottom. Okay? Okay. So remember when we were graphing linear functions, we had this template, y equals mx plus b, right? And that told us what the y-intercept was, and it told us what the slope was, and we used those two things to graph. Well, graphing an exponential function is kind of similar, except that it doesn't have a constant rate of change. There's not a straight line. It doesn't have the same slope every time. Okay, so think of your exponential template, your form here, a times b to the x. Okay, it's a little bit different. Obviously, it's not linear. This is linear. Okay, this is kind of like your slope-intercept form for exponential functions. Except what you know is the first number is the initial value, or the y-intercept, and then the second number is the growth factor. Okay? So we're going to start with the y-intercept just like we do with slope-intercept form. Okay? There's my y-intercept. It's at 4. So I'm going to go 1, 2, 3, 4. Okay? It's actually a point, right? It's 0, 4. But just like with, slope-intercept form, we start with the y-intercept. Okay? Now the next number tells me what to do to get to that, right? So this guy right here is my growth factor. Only we don't add it like in with slope-intercept form. We go up and over. Okay. What we're going to do is we're going to multiply by this number. Okay. So if I'm at 4 and I double it, the next time I move over, I'm going to be at 8. Okay. And then I double again, and then I'm going to be at 16. If I double again, I'm going to be at 32, which is off our charts. Okay, so start here. This will tell you how to get to the next point, but it's not like rise over run. It's just what to do with the previous y value. So I'm at 4, I double it to 8, I double it to 16. All right, so that's our graph. Now, we want to get some more points on this side, and so what we can do is just reverse the pattern, right? If I'm doubling going this way, then if I'm going backwards, I'm just going to do like half. So what's half of 4? It's 2. What's half of 2? It's 1. What's half of 1? It's a half. Okay, so now if we start at the beginning, we go half doubles to 1, 1 doubles to 2, 2 doubles to 4, 4 doubles to 8, 8 doubles to 16. And every time we go over one x value, we double the previous y value. Okay, so this is how our graph looks. And that is how you graph an exponential function. Kind of like slope-intercept form, but different because we're not using a constant slope. Okay, so what you should do on 14 here is you should figure out which of these two things is the initial value, and then start that as your y-intercept, and then use the growth factor to tell you how you're growing. And you'll be able to graph that. So I'm going to leave that one for you. Okay, so lots of examples for you to help you get there if you got stuck. Follow the example, follow the patterns that we saw in the previous one, and we will continue to talk about exponential functions this week and next week. Thanks for watching.